Before we dive in, if you're interested in how block size affects quantization behavior, make sure to check out my other video on that topic. Block size interacts closely with scale factors, and understanding both gives you a much clearer picture of how these formats behave in practice. In this video, we're going to focus specifically on the scale factor and how it impacts the way values are represented in block floating point formats. Here we're comparing the effect of the scale factor in two FP4 block floating point formats, MX and NV. The way we'll compare them is by looking at how a block of numbers gets mapped to the available centroids. If you look at MX and NV, the element formats have very exact centroids. You have 0, 0.5, 1, 1.5, 2, 3, 4, and 6. The same set of centroids exists in both formats, as you can see here. However, given exactly the same input distribution and the same maximum value, in this case 3.609, the values are mapped differently. For example, in NV, you can use almost the entire available centroid range to represent the input distribution. In contrast, with MX, you don't get access to the full available range. You only can use limited number of centroids from 0 to 4, while the highest centroid 6 is effectively unavailable for this input distribution. This is the main drawback of using a power of 2 scale factor. For this example, where the maximum value is 3.609, MX chooses a scale factor of 1, whereas NV uses a much finer grained scale factor of 0.625. This has a direct effect on quantization quality for the entire block. And now, if you look at the quantization error, the maximum difference is much larger for MX. It's 0.391 compared to 0.141 for NV. So what's actually happening here between the two formats? MX uses E8M0, which is a power of 2 scale factor. With a power of 2 scale factor in MX, you first take the maximum value, in this case 3.609, divide it by the target maximum centroid, which is 6, then take the base 2 logarithm and round it up. Because the scale factor is restricted to powers of 2, it changes in discrete steps. In contrast, NV uses a 8-bit floating point scale, in this case E4M3. So the scale factor changes much more smoothly. That's why it can choose a finer grained value such as 0.625. On the top right, the mean squared error across the entire block is shown along with the input distribution below. As you can see, the mean squared error is clearly higher for MX. Now you might ask, is this just a very specific example? Actually, it happens quite frequently. Let's look at another example. Here, the maximum value is 1.898. The scale factor for MX is 0.5, while NV again chooses a much finer value of 0.3125. The same behavior appears again. In the NV case, the maximum value maps to the highest centroid, whereas in MX, the top centroid is once again unavailable. This happens because the MX scale factor has to wait until the input grows enough for the next power of 2 step. Now let's run a full sweep. First, I'd like you to focus on how the scale factors change, and then we'll look at how the available range changes as well. Watch the scale factor values for MX and NV as the animation runs. You can see that the NV scale factor changes smoothly, while the MX scale factor jumps from 0.25 to 0.5 to 1, and so on. That's the fundamental difference. This issue, where the highest centroid isn't used, occurs surprisingly often. A significant portion of possible maximum values causes MX to behave this way. As a result, you lose part of the available dynamic range, and the mean squared error increases. This highlights why the choice of scale factor is so important. A power of 2 scale factor gives you a very hardware-efficient implementation, but you lose the opportunity to fully utilize all the available 4-bit values. In contrast, NV is able to use almost all of the available 4-bit patterns much more consistently. For one final time, let's watch the full sweep again to see how the scale factor changes and how the maximum value is mapped. As the maximum value increases, you can see the black dots moving smoothly for NV, while the MX scale factor stays fixed for a while before suddenly jumping to the next power of 2. So depending on the input distribution that you're trying to represent with MX or NV, you can end up with very different behavior. That's one of the key differences between the two formats. The choice of scale factor matters a great deal. The block size also plays an important role, but that's a separate effect that I covered in another video.